Today we will draw all the number of stereoisomers possible for this molecule 2-bromo-3-chlorobutane. The number of stereoisomers possible will depend on this formula 2 to the power of the number of chiral centers that there are. So here it will be 2 to the power of 2, which will give us 4 possible stereoisomers for this compound. Now how can we find all of those 4? So let's start by drawing our molecule in 3D. Let's decide on a wedge bond for methyl and a dash bond first for hydrogen, just to keep things easy. These will flip later on, but we have to start somewhere. Alright, so based on this conformation, we can tell that our priority groups is going this way, 1, 2, 3. So this looks like it's an R rotation. So we will note that this is an R configuration. What about on the right? It looks like it's going this way. So this looks like an S rotation, and since the hydrogen is on the dash, that is good. So another way to write this is 2R, because it's on carbon 2, this is carbon 1. 2R and then 3S. Alright, so then we have somewhere to start with. The next stereoisomer possible is the enantiomer of this, and there are 2 ways we can do it. We can do it with a mirror image, or we can just swap the bonds. So let's try swapping the bonds here. Okay, so if we swap the bonds, that just means we're going to draw everything the same, except what was on our dash is now going to be on the wedge. So we're going to put CH3 here, H here, H, CH3. Now you'll find out that the direction of priority is still going this way, just the same as last time, so it looks like it's an R. But this time, because the hydrogen is on a wedge, we have to tell ourselves, because it looks like it's an R, it's actually an S. So this is going to be an S, and this is on carbon 2, there is an S. Likewise, on the right, our direction is still going this way, so it looks like it's an S, but it's actually an R because hydrogen is on the wedge, and this is on the third carbon. Alright, so then we have our first 2 enantiomers, and we can tell these are enantiomers because R on carbon 2 swapped to an S on carbon 2, and then S on carbon 3 swapped to an R on carbon 3. So both these chiral centers have swapped. That tells us it's an enantiomer. But now, where can we find the other 2 stereoisomers possible? Well, so for enantiomers, you can have an RS swapping into an SR, and make sure that these are like on the same carbons, all chiral centers swapping from an R to an S, and the other chiral centers swapping from an S to an R. Or you could also start with an R and an R chiral center swapping to an S and an S chiral center. And these are enantiomers, but these 2's relationships are diastereomers. So that means our next few drawings are going to be diastereomers of what we drew in the initial place. So how do we do that? Now, enantiomers swap both chiral centers, but diastereomers only swap one chiral center. So that means, let's just copy what we have in the first place. But this time, okay, I'm going to keep this the same. This time, I'm going to swap this carbon. So I'm going to put the dash and the wedge, but the wedge is now going to be on the hydrogen and the dash is on the methyl. So I swapped this little area. I swapped these 2 bonds, okay? So that means, because this stayed the same, this is still R. I'm comparing it to this diagram. This is still R because it didn't change. But this here now, let's see, it would have changed because, let's see, this is our direction of priority, so it looks like it's an S, but because hydrogen is on a wedge, so it's actually going to be an R. So here we have carbon 2 as R and carbon 3 as R. And then the other stereomer possible is the mirror image of this drawing. So the enantiomer of it. Now in our first example, we swapped the bonds, but this time let me show you the mirror image so that you have some proof that both ways of doing it works, but you can only choose one. So I'm going to draw the mirror image. And let's determine priorities. So this looks like an R rotation, but because hydrogen is on a wedge, so this is actually an S rotation. So this is S on carbon 2, because this is carbon 1. And here, this is our direction of priority. It looks like it's an S direction, and it is an S direction because our hydrogen is on a dash. So this is S on carbon 3. So then we see that here is R and R, here's S and S. So both of these have swapped. So these two are enantiomers, aka they're stereomers. And then these two are enantiomers as well, because all chiral centers have swapped their RS configurations. But the relationship between the top two and the bottom two is that they're diastereomers, because not all of the chiral centers have swapped. The top is 2R and 3S, but down here it's 2R and 3R. So this stayed the same while we swapped this. So that's how you determine all the stereoisomers possible for a molecule.